Welcome to Lecture 7. It's going to be about dynamics of quantum systems that interact with the environment, and we will be interested in self-contained description of this dynamics. So the reason why we are interested in understanding how systems that interact with everything else, how they evolve, is simply because our wonderful quantum devices, real quantum devices, will be embedded in some sort of environment with lots of noise, lots of interactions that we cannot control. And the question is, how are we going to deal with that? But before I'm going to tell you how we are going to deal with that, so before I'll discuss quantum error correction, first I have to, of course, give you some sort of idea how to describe open quantum systems. So before we start, I would like to remind you about our journey, so how to place this lecture in the context. So remember, we started with 4 introductory lectures. So they were all about quantum interference, about quantum entanglement, how to calculate probabilities in a new way, and we then discussed the power of quantum interference and quantum entanglement in the context of quantum cryptography, secure communication, but also in the context of quantum computation. So we know that quantum interference and quantum entanglement, because we do have subsystems, remember, subsystems plus quantum interference gives you quantum entanglement. We could see that the power of quantum computation comes really from a clever use of quantum interference. So now, when we have those systems embedded in an environment, so if you think about a situation that you have an environment, we call it E, and our system of interest now, S, is embedded in the environment. So it just interacts with this environment. There's lots of interactions where it really cannot control. If we could take everything, absolutely everything into account, then of course the evolution is unitary, because then that would be an isolated system. And so this would be some sort of unitary evolution, but so the system and the environment. But then if you look at the individual subsystem, the system of interest, so here S, and ask yourself question, okay, how shall I the evolution of the system S from here to here without necessarily referring to the environment and all those interactions that we don't know about? Is there any specific form we should write these interactions? It will probably not be unitary. You can guess that right away. Yes, it will not be unitary. It can be, but usually it is not the case. So, so in terms of a diagram, you may think about the following scenario. So we have a system of interest. So that's our system of interest. Initially in some state, say psi, an environment. Initially, we'll assume it's not in any way correlated with the system in some other state, E, and then there is a big unitary evolution of everything. And at the output, you get something that is entangled, and you don't care about the environment in this case. So you drop the environment, so you trace over the environment. And what you get here is something, right? So there's some, in general, density operator. Let's write it rho I, describing the state of the system. So once we fix U and the initial state of the environment, there is a well-defined map that takes you from the input state here, the psi, the state of the system, to the output state rho prime. And so we would like to figure out how to write, to characterize those maps. So we want to know what kind of mapping we have that will take, in general, the density operator. It could be a projector on psi, but in general, rho into rho prime. And you will see that, in fact, this rho prime can always be written as the sum over k, and then there will be some operator E sub k rho e dagger sub k, where we will require that there will be a requirement on those operators that the sum of e dagger k ek is equal to the identity. So that is like, if you look at this expression here, you can think about it as some sort of a way of generalizing unitary evolution. So remember, the unitary evolution of this density operator would look like this. So that would go, rho would go to rho prime, that would be equal to u rho u dagger. And of course, you know, this is unitary, so you have only one term here, u dagger u is equal to the identity. But now we just don't have one term, but many operators. They are not unitary operators, so our initial density operator is sandwiched between those two operators that, as you will hear in a moment, they are called Krauss operator. And so that's like a preview, but of course, you know, I would like to tell you about different ways of describing this, call it subdynamics, right? I would like you to see the Krauss operator picture. I would like you to also look at it from a more mathematical point of view and see it as a completely positive trace preserving map. And I would also like to characterize in a slightly different way in terms of the so-called the Choi matrix. So there will be lots of name dropping, right? So you have Krauss operators, you have Choi matrix, and there will be probably a few more, but remember, just don't be intimidated by names. Actually, the concepts are very simple. And so let's go through this, and that gives us sort of a good preparation for the formulas that we need for the quantum error correction.